As a first example, let's consider the matrix A equals 3, 5, 1, 7. This matrix gives us the equation AY equals Y prime, where this matrix equation stands for this system of equations. Y1 prime equals 3y1 plus 5y2. Y2 prime equals 1y1 plus 7y2, here and here. Our equation then is that it says that y prime, which consists of excuse me, the vector y prime is equal to this matrix multiplied by the vector y, where the vector y is the vector that consists of the column y1, y2, and we've seen that, and that y prime is just the column vector y1 prime, y2 prime, where these y's that don't have arrows over them are completely different than these y's that do. A y with an arrow over it indicates that we have a column vector of scalar functions y. Now the equation that we're going to consider is this equation with the initial condition that y of 0 equals negative 2, 3, meaning that y1 is negative 2 at 0. The function y1 of 0 is negative 2, and the function y2 at 0 is equal to 3. So we could write that in here. We could say y1 of 0, did I leave myself room, equals negative 2, y2 of 0 equals 3. Now that's written really small. You might not be able to read it. We start with our assumption that y of t is of the form e to the lambda t times x1, x2. And that leads us to the solution, or to the matrix. And this is the matrix A minus lambda I, and that matrix is going to be 3 minus lambda 5, 1, 7 minus lambda. Be sure you understand why, if you subtract lambda I, where I is the 2 by 2 identity matrix, from this, you get this. Okay, now what do we know? We know that we're going to get a solution to this equation if the determinant of this thing is non-zero. Well, the determinant of A minus lambda I is just 3 minus lambda times 7 minus lambda. Do I have room? Minus 5. And that's the equation lambda squared minus 10 lambda. Then it's going to be plus 21 minus 5, which is going to be plus 16. Now, solution exists. Well, okay. This determinant is equal to 0. Remember, the determinant has to equal 0, so that this matrix is non-singular, so that we get non-zero solutions to the equation that we didn't write here. This equation factors, we could have used the quadratic formula, but it's fairly easy to see that this equation factors into lambda minus 8, lambda minus 2 equals 0. So we get two values. Lambda 1 equals 8. Lambda 2 equals 2. Now each of these solutions to the equation should then lead to a solution to the differential system. Now the equation from which we got this determinant is A minus lambda I times x equals 0. Let's write it out. That equation would be the matrix 3 minus lambda 5, 1, 7 minus lambda multiplied by x1, x2 equals 0, 0. Now for lambda equal to 8, we substitute 8 for lambda, and we solve the equation for x1 and x2. We've got our eigenvalue. If we can solve for x1, x2, that'll give us an eigenpair, so we can form a solution function. Okay, I wrote this equation down carelessly. That's 3 minus lambda, not negative 3 minus lambda. So if lambda 1 equals 8, then 3 minus 8 is negative 5. So we get negative 5, 5. And 7 minus 8 is negative 1, so we get 1, negative 1, multiplied by x1, x2 equals 0, 0. This translates into two equations. Negative 5x1 plus 5x2 equals 0, and x1 minus x2 equals 0. These equations are degenerate. This equation, or let's say this equation, is just negative 5 multiplied by this equation. The equations have identical solutions. Any solution to the first is a solution to the second. And for 2 by 2 systems of two equations, that's generally going to be the case. These two equations are always going to have to be degenerate. They're always going to have the same solution. And if they don't, then there's a red flag, and you need to take a good look at what you're doing. Now, any solution for x1 and x2 will do. So any solution is okay. So let's choose write it this way. I'm running out of room, so it's going to be kind of x1, x2 equals 1, negative 1. If x1 is 1, x2 is negative 1, we can, whoops, hang on, something wrong here. Said that wrong and wrote that wrong. This is going to be 1. x1 and x2 have to be equal in order to make either of these equations true. I wrote that carelessly. And then our second eigenvalue, lambda 2 equals 2, gives us the matrix equation. 3 minus lambda is 1, 5, and down here we get 1, 5 once more. This gives us the equations, and both equations are identical since these rows turn out to be identical. Here the rows are multiples of one another, but here they're identical. And we're going to get x1 plus 5x2 equals 0, so that, let's put it this way, x1 is going to equal negative 5x2. Choose x2 equal 1, so x1 equals negative 5. And we get, try to make that look a little less sloppy, we get x1, x2 equals negative 5, 1. This gives us eigenpairs. For lambda 1 equals 8, our x vector is 1, 1. For lambda 2 equals 2, our x vector is negative 5, 1. So we can write this as follows. We have eigenpairs, eigenvalue 8, eigenvector 1, 1, and 2, eigenvector negative 5, 1. these eigenpairs, each eigenpair gives us a solution. Of the form e to the lambda t times the x vector. And the solutions then are e to the 8t multiplied by 1, 1, and e to the 2t multiplied by negative 5, 1. The eigenvectors, eigenvalues are distinct. Implies the eigenvectors are linearly independent, which implies that the solution set e to the 8t multiplied by 1, 1, e to the 2t multiplied by negative 5, 1 is a fundamental set. The general solution, bad looking G there, but we'll have to live with it. General solution is C1 e to the 8t times 1, 1 plus C2 e to the 2t multiplied by negative 5, 1. And of course we could write that as a single vector if we want. That's C1 e to the 8t minus C2 minus 5C2. How are we going to repair that? Let's see, minus 5C2 e to the 2t. Doesn't look great. And C1 e to the 8t plus C2 e to the 2t. We'll proceed in a minute with a short clip where we use the general solution to apply our initial condition and find the specific solution of this equation that satisfies this initial condition.